Okay, well, we're 4 minutes past the hour, so we're going to get started. I'm going to start by introducing myself. My name is Julio Zimbron. I am with E-Flux. E-Flux is a small startup company that has been around for about 2.5 years. E-Flux uses a proprietary technology developed at Colorado State University by myself and other researchers, and now licenses the technology from CSU. In addition of being with E-Flux, I am also affiliate faculty with CSU, and we also have here helping behind the scenes Gabriel Rodriguez and Emily Cassion with E-Flux. So we got, about 50% of people signed up for this, and I got a few cancellations. So we have a significant portion of the people that sign up, and we're going to get started on this. So the presentation will be based on a recent paper that is still online with groundwater. It hasn't made it to a written version of it, but it's in the queue and it's available online. And this describes the technology and one of the first pilot tests that we did using it. I've been working with this technology for about 5 years, 3 of them with CSU, and now in the last 2 years through E-Flux. There's additional materials that we'll be referencing in this presentation. There's a lot of work from previous research done by Dr. Paul Johnson at Arizona State University. Some of that work is included in the ITRC guidance document for LNAPL. And there's also another line of work, very important line of work from the University of British Columbia, the group of Dr. Uli Meyer. And there's also additional current research conducted by, I believe this is sponsored by an oil company about using temperatures. So the presentation is really intended to be an extension of the materials that are discussed in the ITRC class. The class is meeting three times a year. And E-Flux is a sponsor of the class, and the intention is to give you a little more than what a class offers and provide you some additional materials in case you're considering natural source on depletion. So in terms of background, I'm going to start with a bit of a background on the problem that we're looking at. And then dwell into some of the alternative technologies to do these measurements of natural source on depletion. And in the end, I'm going to offer some case study data and also some current research, and then we'll open it to questions and answers. So if you have a question through this presentation, please type it and type that in the chat, and we'll collect those and try to group them by themes and answering them that way. If we don't get to your question, we will try to compile all of the questions and come up with some written document that is circulated back to the attendees. So in terms of the background of the problem, this is a conceptual site model of a petroleum contaminated site. There's an oil spill. It sinks through the vadose zone until it finds the water table. Then it floats because of its lower density. Part of it dissolves into the aqueous phase, generating what is known as a plume. However, there's also biodegradation reactions, and these biodegradation reactions, mostly methanogenesis, is known to generate CO2 and methane. CO2 and methane are both gases, so these gases have high mobility and start generating some kind of cloud that moves away from the source. And as it moves away from the source, really the natural destination for these gases is that they're going to daylight. However, the methane is also reactive. The methanogenesis is anaerobic, and when the methane encounters atmospheric oxygen, it easily reacts. Microbes love to use methane as a carbon source when there's oxygen present. So the methane itself turns itself into CO2. So the result is that a lot of the byproducts of biodegradation show up at ground level as gases. And there's a really nice study from the University of British Columbia. It's a model, and they evaluated the possibility, the transport of these gases through the vadose zone, and the possibility that there was an accumulation. And this really good work shows that most of the gases that are produced in the biodegradation zone show up at ground level. So there's really almost no accumulation within the vadose zone. Here on the right, we have a picture. This is a picture that we took from a petroleum-contaminated site. It's a core, and the petroleum was in the order of 10 to 15 feet. And this particular section of the core was, it shows that it's black, and it's black because the sulfate present in the groundwater has been used as an electron acceptor and turned into sulfide. Metal sulfides readily precipitate and generate this black material in the soil. If you look closer in this picture, you will see some small bubbles of gas. This is really biogas, and if you put this core into a Ziploc bag, into a sandwich bag, and put a gas detector in it, you will see that it's really high in CO2, and it's also very high in methane. So the lesson here is that biodegradation of petroleum produces biogas. So how do you monitor this process? How do you measure them? There's multiple alternatives. The earliest method is called the gradient method, and the gradient method establishes that if you measure soil gas concentrations in the vadose zone, and then you can use the change in concentration with location, the gradient of concentrations, combined with fixed second law of diffusion, and estimate the flux that way. That's really the earliest indication. This is reflected in the ITRC guidance document, and it was really a breakthrough because people were used to measure concentrations of compounds, but what this told you is you should be looking for fluxes. So it changed the paradigm from measuring concentrations to measure fluxes, and it also provides you with a tool to do that. More recently, the University of British Columbia developed this idea of using an agronomic technique called the flux chamber. And the flux chamber really is it's a closed container, really something like a bucket that you put on top of the soil, and as there's flux of soil gas into the bucket, the concentrations inside that container change. And by measuring the change in concentration with time, you can estimate the flux into that chamber. There's different versions of this method. The model is not proprietary, but there's different versions of it, and there's different ways of using the mass balance to estimate the fluxes. And then about 5 years ago, we had this idea at CSU that if you capture cumulatively the gases as they come out of the soil, then you can estimate the total mass. And if you know the area from which you capture the gases and the time for doing the measurement, you get the long-term average. Most of nearly all of the experience that we have is with this method that we call the CO2 traps. So the ITRC, so these are ways of measuring the natural source of depletion based on gases, you can also go, the ITRC guidance document also has a methodology to estimate the degradation rates based on the electron acceptor use. So if you know how much water is flowing through this area, and you know how much, what is the mass of electron acceptors or degradation byproducts in that water, you can estimate a flux. People have been trying to do that. Typically, the numbers are relatively small, and my impression is because it depends on what is driving the reactions. And methanogenesis seems to be a major process rather than direct electron use acceptors such as sulfates or iron or any others. So the byproducts of biodegradation are in the gas phase, and really methanogenesis does not need any external electron acceptors. So I'm going to start with a brief description of the gradient method. The gradient method, as I indicated before, has been mostly developed by Dr. Paul Johnson at Arizona State University, and this states it takes advantage of a fixed second law of diffusion. J, which is the flux, and its mass per unit area per time, is equal to the effective diffusion coefficient times the change in concentration with elevation. Here we have an example. This is from a 96 paper by Dr. Johnson, by Lundegaard and Johnson in 2006, I'm sorry. So this shows the concentrations of CO2, methane here as squares, and the circles are oxygen. So it tells you that these changing concentrations of CO2 are what you would use for this estimate of diffusion. So that's relatively the easy part. So if you go to the field and you measure these concentrations, you could use them to estimate fluxes. However, you also need the site-specific effective diffusion coefficient. And that is a little bit tricky because it depends on the properties of the gas, but mostly on the properties of the soil. So you can go to a field site, get these concentrations, but you also need to do an estimation of this number, the effective diffusion coefficient. This is a bit labor intensive. You need individual sampling ports in the vadose zone, and then you have to collect the data and do a fair amount of work to estimate this diffusion in situ diffusion coefficient. You need the soil transfer properties. And this measurement of the effective diffusion coefficient needs to be at the same time as the time when you took these concentrations, because it changes quickly. It changes with moisture and temperature. This model is rigorous, but it assumes that there's only diffusion. And so if anybody has had experience opening a wellhead and getting kind of a gush of gases, well, that is an indicator that there's a pressure buildup. And it is possible that the gas is being produced where the contaminants are creating an increase in pressure. So that is advective flow, and that is not accounted by this model. The other thing that this model assumes is that that the species that you're measuring is non-reactive. For example, right here to the lower right of this plot, you see that the carbon dioxide, CO2, is the concentration is not going down, and it's probably because it's being produced in this interval. So don't apply this equation when there's evidence that it's reacting. Interestingly enough, we see that the methane is decreasing in concentrations at the same time that the CO2 should be decreasing but remains constant. So be careful about advection, advective flow, and also when reactive species are present. As I indicated before, this is what is included in 99 ITRC guidance document, and it's useful. It tells you also where processes are happening, which the other two methods don't do. So the second alternative to do this is the chamber method. The chamber is this cup on the right. It's this white cup in this case, and it's connected to a soil gas meter. So you deploy this cup on top of a receiver pipe that makes a seal with the with the ground, and how these concentrations change in the cup tell you how much flux there is into this cup. The cup is vented. There's different versions of this. The original was not vented. Turns out that having this vent is important. You deploy this cup, you can get the fluxes at the time of deployment. The deployment of the of this chamber is typically in the order of 5 to 15 minutes. So this number, it tells you what is happening at the moment of the measurement. However, there's different processes such as barometric pumping in which if the ambient pressures change, the fluxes that are associated with that location can suddenly change. These are plots of fluxes measured at different locations, 9 different locations, for 24 hours. And what this shows is that some of these flux, this shows the 24-hour variation. We see that there's a high flux towards, the 17th hour from the start, and the fluxes are negative at night. So if you really want to characterize the long-term measurement of fluxes, you need to get the full-time series. And that is a little more than what this technique was designed to do. You can do that by deploying this chamber over and over for an extended time. There's an attachment that does this automatically, and the other thing is that you really get the total flux. This is a field measurement, and it's hard to do carbon isotopic work. It's possible to do that, but you have to take multiple samples through the deployment of this chamber. So my opinion is that this is a really good tool, but it's perhaps best used to screen different locations and to get a single snapshot in time to identify what is happening in the field. This is one of the other advantages is that you can easily adapt this tool to other gases, for example, methane or VOCs if you have the right sensor. It also measures the total flux. For the open-top version, you can measure the total flux, which is that from advection and diffusion. So here we have this technique that we have developed at CSU, and the technology is very simple. It's a cartridge with 2 layers. In fact, let me switch to this slide right now. Because it's a cartridge with 2 layers, it has a lower layer of sorbent in yellow in this slide. And what this cartridge does is sorbs CO2 as it leaves the ground. However, we recognize that the species that we want to measure CO2 is also present in ambient air. So we added a second layer that keeps the interference from ambient air away from the lower layer, which measures what we care about. This thing in blue right here is just a spacer, and this slide right here shows how it looks in the field. This is a new version. We're on the 3rd version of this. This one it's a smaller footprint and shorter also, and the field efforts are relatively simple. You just put a receiver pipe and you deploy your cartridge. The cartridge stays in the ground for about 2 weeks. It doesn't have moving parts and it doesn't need any power. So after the cartridge is deployed for about 2 weeks, it gets retrieved from the field, closed, and sent back to the lab for analysis. So what we do is the total carbon analysis, which is the total carbon flux. It's the time integrated flux over the period of deployment. And we also do carbon isotopic analysis routinely. We use carbon dating analysis to estimate what portion of the carbon really came from fossil fuel and really remove the interference from modern carbon. Because the cartridge bed, the sorbent bed is porous, highly porous, it really offers no resistance to flow, so it measures both diffusion and advection fluxes. The disadvantage of this technology is that because we do laboratory analysis, it takes about 4 weeks from the moment it's retrieved to get a number. So this slide shows some of the earlier tests that we did to demonstrate that the analysis was quantitative. We started with a closed system. we were flushing a nitrogen stream through a bed of the sorbents here, and on line we were adding a known amount of carbonate that was released by acidifying it into the nitrogen stream. So we got quantitative recovery. Then we moved to large column experiments about 2 feet in diameter. We put, this is the second version of the trap in this picture, and we put triplicates, and we got good recovery. We started these experiments at high flow rates, and more recently CSU has completed a study in which the flow rates are smaller, more representative of field fluxes, and we get, again, quantitative recovery. So once we did this first prototype validation in the lab, we started with 6 initial pilot tests. There were 3 former refineries, 2 active refineries, and 1 rail yard. All in all, there were in the order of 100 sampling locations, but because we sampled many of these locations multiple times, they were in the order of 200 CO2 trap measurements. Some of the earlier measurements really were only for total carbon, and only later on we added the C14 analysis or carbon dating. This is how the deployment looks like. You put your receiver pipe, and then you put a coupler, a rubber coupler, and then you drop the trap into the coupler. So, so in the next few minutes, I'm going to describe one of the earlier pilot tests, and also some of the uses of the data. So before I go into that, I want to describe a change in units. We have 2 different types of units. The strict CO2 flux measurement is mass of CO2 per area per time, and the agronomic units for that are micromoles per meter square per second. However, practitioners think in other terms. They think in terms of hydrocarbon volume, or some other units that are more related to the performance of active remedies, such as gallons per acre per year. So how do we go from one unit to the other? We just make a very simple assumption, that is that a single mole of carbon in petroleum generates a single mole of fossil fuel CO2. So we also assume the density of the hydrocarbon that's typically available from site data. And if not, we use a generic one, and really this assumption really only makes a difference of about 10% at most in the estimate. The second thing that we do is we need to acknowledge that the number we're measuring is a fraction of the total carbon, and there's 2 ways of doing that, which I'm going to describe later. So this is data from the 6 initial pilot sites. These were background corrected. So we did measurements of total CO2 flux at background locations, and we subtracted that number from the numbers we're getting from impacted location. And again, we changed those numbers to the units of gallons per acre per year. These are box and whisker plots. They describe the data at each site. Each box describes that, and it has a 25, median, and 75 percentile of the population. It has the average as this circle in the middle, and if there's and the standard deviations are shown as these whiskers. That's why they are called box and whiskers plots. And if there's any outliers, they are shown as individual asterisks. So what this shows is that really the numbers are fairly high commonly in all of the sites. The average across all sites was in the order of 3,500 gallons per acre per year equivalent. And again, this is the background corrected number. And the numbers were really large, perhaps even hard to believe, but we did triplicates in some of these high numbers, and we got good reproducibility. So the lesson here is that natural source and depletion is widespread throughout sites, and the number of that is in the order of 1,000 gallons per acre per year is not uncommon. We often we looked at how does this number compare to the long-term longevity of the site, and even a high number such as 1,000 gallons per acre per year translates into really only about a millimeter of free NAPL thickness. So if you have feet of petroleum, you can explain longevity that is decades long, that that is consistent with these numbers. So this is one of the earlier pilot studies. Now this is what is in the groundwater paper that is still on the internet, hasn't made it to a written to a hard copy. This shows the gallons per year equivalent losses. We had 3 locations. We took the total CO2 flux and we subtracted that from the other numbers. So some of these numbers are really small. They become really null, and some of them are in the order of 1,000 gallons per acre per year. And this triplicate here is really unusual. It's in the order of 10,000 gallons per acre per year equivalent. In fact, there's a triplicate there because the first number that we found there, we didn't believe it. So there's some local effect at this area. It could be perhaps the groundwater temperature. I'm going to show some data that suggests that that's at least one of the factors that can be contributing to this high number, although there could be others. So this is the same side map, and what this shows are the numbers that we measure, the background corrected numbers, but it also shows the groundwater temperature. This is the maximum groundwater temperature within a well. So Kevin McCoy, the student that completed his master's on this about 3 years ago, he went and dropped a thermocouple in the groundwater, and the lowest temperatures are in green. They move through yellow and orange and red for the highest ones. And we see that a lot of the highest numbers are really corresponding to the highest fluxes. When we plot the temperature, the maximum groundwater temperature against the fluxes, we see that the highest numbers happen to have in the order of 4 centigrade degree higher groundwater temperature. This is consistent with microcosm data. This is a paper that CSU published by Seaman and others in last year in the journal Biodegradation. So what this tells you is that the degradation rates are higher until you reach a temperature of 30 degrees or 35, and then the microbes get inactivated by the heat. So I'm going to move on to describing the use of carbon isotopic analysis. And I mostly will describe, there's really 3 carbon isotopes that are major in this work. There's a regular carbon isotope, which is C12, and then there's C14 and C13. C14 is important because it's a tool to date the age of the carbon. Let's see. So C13 exists in ambient CO2. And it's created by cosmic rays in the atmosphere, and it's so the concentration in the atmosphere is typically constant. It's unstable. It has a half-life of about 6,000 years. So by the time that it becomes a fossil fuel like petroleum or coal, for that matter, there's no C14 left. And this fact is used to use a 2-source model. So if you have this modern carbon, the source A, that has a delta C14 of typically in the order of 150 per mil, and you have a source B, which is fossil fuel, that has no C14, and you mix them, you can back calculate the contribution to the mix from each one of the 2 sources. So in this almost trivial example, if the delta C14 of the sample is 75 per mil, it's half of the source A. That indicates that both sources would contribute equally with 50%. So this is the basis for an ASTM method, and that's what we use to routinely remove the interference from modern carbon into the samples we collect. So there's really 2 approaches of accounting only for LNAPL-derived CO2 flux. One is the C14 analysis, what I just described, and there's also this approach called the background correction. The background correction was one of the earlier ones. There's this paper on ES&T by Natasha Zihora, and who was at the time with Uli Meyer's group at the University of British Columbia. And he acknowledges that the total flux of CO2 is the contribution from the natural flux and that coming from the contaminant degradation. So that is the background correction. And then you have the alternative of using the C14 analysis to estimate that. And what this plot is showing is a comparison between the two approaches. We have 4 sites, and for each site we calculated both of these modern carbon fluxes per the 14 analysis on the left, and on the right we have what the background correction is by the second alternative. So we have, for the first side, we have the box and whisker plot again, and we have what was used as a background correction. Of course, there was only one measurement for site A, but this shows that there's a widespread modern carbon flux, at least on this site. In the second side, we get also the box and whiskers plot. They show a similar distribution of both the background correction and the fossil fuel correction. In site C, there's a very strong difference between both approaches. So this is the correction itself. This is what the interference from modern carbon. So in this slide, what I am showing is the same interference that I just described and the final results using both approaches. Again, on the left, we have that from the carbon isotopic analysis, and on the right, the numbers that you will get if you use the background correction. What this shows is that if you compare within every site from left to right, there's almost always, there's nearly always much higher variability using the background correction. So this tells you that the modern carbon processes are very site-specific, are highly location-specific for every site. So the background correction assumptions need to be checked before you should use that data. In fact, in some cases, you get negative fluxes if you use the background correction, and in almost all cases, it results in higher variability. This is a plot from an agronomic journal that shows you the natural soil gas flux throughout the year for multiple years at an agricultural site. And there's a maximum through the middle of the year, and it's highly variable. It changes with a year. So in addition to temporal to locate the variability due to specific location, there's also the temporal variability. So I am going to switch gears here, and I'm going to go into the data use. How should you take this data? We started really with the box in the middle. We started quantitating these natural source and depletion rates. But more and more, it seems to me that you shouldn't be using this data just by itself blindly. You need to develop a conceptual site model. You should be using screening tools that tell you what is the geochemistry at each one of these locations and if it's consistent with the numbers you're getting by quantitation. So there's you can do shallow soil gas surveys. Those are extremely useful. You should also be measuring wellhead concentrations. There's a really nice paper by Dr. John Wilson about how to do the measurement on wellhead space. And you should look at the groundwater geochemistry and certainly groundwater temperatures. And you should do this iterative process to inform your site conceptual model and use all of these data integrated as a whole. So you checked your data, your quantitative data, against your lines of evidence. One important piece of the puzzle here is LNAPL mobility. In order to make the case for having NAPL that has been recovered to the maximum extent possible, you probably also need to look at the mobility of the NAPL. As I indicated before, we started with 6 pilot tests at CSU. We conducted in the order of 18 at CSU before technology was migrated to E-Flux. This slide is not updated. So far, we have in the order of 50 sites done through E-Flux in the U.S., Canada, Australia, and we have additional ones now coming in the UK. So we have a fair amount of experience with these measurements, and they have proven to be fairly useful to develop site conceptual models. So how can the data be used? We the first one, and perhaps more obvious, you use this signal coming from petroleum to map hydrocarbon sources. It's not what we started with. We started trying to quantify the natural source and depletion rates, but this mapping is a potential use for the data. The second one is the one that I just described as more obvious. We were trying to quantify the rates of natural source and depletion as a remedy. And typically, you also have to look at this carefully about whether or not there are other criteria that are met, such as the lack of migration. There's a lot of documents from the regulators that tell you when is natural source and depletion or natural attenuation something that you should consider. The third one is that you can use the performance of this natural remedy to compare active remedies, particularly when the active remedies have plateaued in the performance. If you have been working with hydraulic recovery and soil vapor extraction systems, and they have worked for a number of years, but now you are wondering if they are if they're being useful and achieving a meaningful depletion of the source, then you can, it's very easy. People know how these active remedies perform, so you can just do a natural source and depletion and put them side by side and see if it still makes sense to continue the active remedy or if it has achieved period of diminishing returns where you can perhaps use natural source and depletion and achieve even as much as the active recovery. The last one is really a research. It's more of an idea. I don't have any case studies on this, but if you have active remedies that achieve the full mineralization of petroleum, such as chemical oxidation, mineralization means that you're generating CO2, and then it becomes the same problem that we are very familiar with. If we measure the flux at ground with these tools, you should be able to estimate the performance of these active remedies. So we have a few cases of regulatory acceptance. This particular came from Colorado, and what they did in this case, they look at the NAPL mobility by measuring the velocities of the NAPL through the wells, also using technology developed at Colorado State University by Dr. Tom Sell, but in combination with a trap. So they estimated that the rates that needed for a stable plume were the measure rates were higher than those that were needed for a stable source, and in that regard, it was estimated that it posed no significant risk. So I want to look back and talk a little bit about the limitations of these numbers. Before I get into this slide, I want to point out that just like every other measurement in groundwater, there's a uncertainty related to all of these measurements, and uncertainty is really related to a lot of the assumptions that are taken. When we started, so we're measuring natural source and depletion rates by really looking at gas transport, and we're assuming one-dimensional gas transport. So that means that the gases show up daylight at the same right on top of where they are generated. However, if you have a permanent capping, such as concrete, then the gases are not going to be able to show up where they are produced, so they have to go around the concrete and daylight somewhere else. My impression is that in most cases they still have to daylight, and at that point you can look into redefining your control area to try to do a mass balance on that. It's not as straightforward as if this cap was not there, because then in that case you can typically just overlay your measurements over the impacted area. So permanent caps are to be avoided or need to redefine control area of the ground surface. There's also unexpected temporary caps. If you have a clay lens in the vadose zone and it's dry, it will not be an impediment to gas transport as long as the pores are full with gas. However, if there's a heavy rain event and that clay soaks a fair amount of water, it will saturate and will act as an impermeable barrier to gases. So in that case, the microbes are probably not going to care about that additional moisture. If feet or 10 feet away from them, they're going to continue to do their thing, and the gases produced are going to migrate sideways until this path for gas transport is restored, and they can daylight again through the shortest path. So I'm reaching the conclusions here. We have a fair amount of experience, a number of years using these traps. The design is very simple. It's very easy to use, and it's relatively robust. It provides time-integrated measurements for weeks at a time. The fact that the samples are analyzed in the lab enables very easy to do isotopic analysis and account for the interference of modern carbon sources that is site-specific. What we have learned is that the CO2 fluxes are large and indicate significant LNAPL losses. These also always should be cross-checked with other lines of evidence at these locations, such as whether or not there's petroleum, what are the soil temperatures, are they consistent with an exothermic thermic reaction, is the soil warmer, where the degradation rates are higher, and when available, soil gas concentration by permanent sampling ports, wellhead space, or temporary soil vapor points should be also checked. Lastly, you should always check the model assumptions, particularly this transport deal, about whether or not the transport path is available between the source and where you're making the measurement. I have a few additional slides about research. I probably have more slides than what I have time. I don't want to spend more than 5 more minutes on this. But I'll talk about a few other things that have been going on. CSU, headed by Dr. Tom Sell, has been doing modeling and lab comparison between the different methods. And I'll let you hear the story from him, but I think that it seems like when the conditions are ideal, meaning that there's no wind, there is a good agreement between the chamber and the traps. The gradient seems to be underestimating the measurement. It's probably because it's not accounting for advection. However, when we switch to non-ideal conditions, when there's strong wind, there is a venturi effect that could bias the chamber measurements low and the traps measurements high. How high? It depends on the wind. So always check the weather. We also have a new improved design that is it's much smaller, much shorter than the previous one, and that will minimize these effects. We're looking also at the use of carbon isotopes, C13 as a screening tool. The reason is because C14 is fairly expensive, and if we can use C13 as a screening tool, we might be able to offer a less expensive version of the measurements as a screening tool. We're working on additional trap applications. We are working on a flux trap for VOCs, and that could be applicable to soil vapor intrusion. We're also working on measurement of greenhouse gases, being methane and nitrous oxide. We're starting with doing chamber measurements on these, but we are also developing a sorbent for nitrous oxide. And there's additional amount of work in terms of using the thermal signature of the biodegradation reaction to estimate the rate of biodegradation. So in a couple of minutes, I'm going to touch on the C13. This is an earlier paper by Rob Hinchy and Pradeep Agarwal in early 90s, I believe. And what they show is that the C13 signature at unimpacted locations on the left of each line, and then at impacted locations. And there seems to be a shift, and it's because the petroleum has a C13 signature of minus 28 per mil. And background should be much should be a less negative number, a smaller number from minus 18 to minus 26 per mil. So that poses the question: can we use C13 as a surrogate for C14 using a two-source model analysis? That's what we've been looking at. This has 6 sites. On the x-axis, we have the C14, the fossil fuel numbers per the C14 analysis. On the y-axis, we have the C13 analysis, and we're correlating both. And there's a strong correlation in all sites. We're also looking at there's a few outliers, and what we're doing is we're looking at some kind of a success estimate. Predicted top quartile locations with the highest fossil flux, and these numbers are, not perfect. 4 out of 6 in a few cases they are pretty good for 2 of the sites, but in 2 other cases they missed the locations with the highest fossil fuel. So it could be used perhaps as a screening tool, but the success rate is not perfect. And this correlation, by the way, is highly site specific. The slope of these lines are site specific. So this is getting into the soil vapor intrusion problem. I am not going to go into this. I think I'm just going to end the slides here. I'm going to tell you really quick that there's potential of using the basic idea of the traps, the 2-layer configuration, put it on a man-made fracture and estimate the flux in and out of the house. Because those fluxes are mostly driven by advective fluxes that are governed by the house pressures. So I'm just going to leave it here. If anybody else is interested in anything else than what I've mentioned as future work, please contact me, and I'll be happy to give you more extended versions. But now, at least I want to leave a little bit of time for questions. Let's see. We don't have that many questions, so we encourage you to type any questions that you might have. Otherwise, we're just going to go through the single question that we have, which is the cost. The budgetary cost is in the order of $1,500 per location, and this includes the use of the equipment and the analysis, being the total carbon analysis and the C14 analysis. And we generate a report that essentially tells you what is the fossil fuel flux at each one of the locations. We have a question here about why doesn't the CO2 convert to the carbonate ion under neutral pH? It does. However, well, I understand if this is a question about how we do the measurement or if this is a question of this reaction in soil. But I'm going to touch on how we use this reaction to do the measurement. The sorbent is really a strong base, and carbon dioxide is really carbonic acid. So when carbon dioxide passes through the sorbent, it becomes carbonate and it becomes stabilized. And that's a reaction that we use to do the measurement. So it does change, and we use that reaction for the analysis. So what's the strategy for evaluating a site with a 20-feet clay layer over several hundred acres with contaminant sand aquifer below? That's a really good question. I would say that I would track the moisture in the soil. The clay layer might not be an impediment for flow as long as it's dry. We have a number of sites in which there's a clay layer, and we get a strong signal at ground level as long as that clay layer hasn't received 2 or 3 inches of rain recently. So the moisture in the soil is to be checked, and in this case, I would say that this screening tools should be very useful about letting you know to what depths you're seeing a signal from either CO2 or methane, and whether or not if you're losing it at a certain depth where the clay is. I would say that the cases in which the gases don't make it through clay have been an exception, perhaps because we mostly have been dealing with those clay examples in in dry climate. If the clay layers are discontinuous, then that's a different animal. That's even if they are wet, the gases are going to go around and daylight not too far away from where they were generated. So now I'm going to move on to the next question. Can you apply a correction for either a groundwater monitoring well or a soil vapor monitoring well extraction well, both in a capped and uncapped version? That's a really good question. There is I avoid really going to wells because the well is really continuous disturbance of the vadose zone. So it's my impression of a well is that it really is an invitation for short-circuiting the gas flow to the well. So, however, there's people that have done measurement in wells, and what they do is they estimate a radius of influence. There's a NSZD project in which the researcher, his name is Thomas Boyd, he was exactly doing that. He was estimating the CO2 fluxes in the well and estimating with the use of models the radius of influence. I don't think it's straightforward. I think it adds uncertainty to the measurement, but people are doing it, and my preference is really to try to avoid going to wells and do the measurement, and try to deploy them on disturbed soil and try to minimize the soil disturbance. So here's the question. The question says, how many sample points over a certain area would you recommend? I would say that's $1 million question. I don't have a good answer for that. It depends on the extent of the NAPL and the site heterogeneity. Here, I think this is a decision that should be informed with screening tools. I saw a presentation by Natasha Zihora at the last Battelle conference, and she looked at a really high data density using the chambers, and she looked at something called a variogram, estimating, once you have a large data set, reducing it and seeing for how much can you reduce it and essentially get the same number. And I understand that paper is going to be out for publication, and that should be a very useful work. Now, have you evaluated how the sulfates or DNAPL contaminants such as chlorinated ethyns or OCPs might affect the natural attenuation rates of CO2 flux? No, that is a good question. When you have a co-contamination of chlorinated solvents and petroleum, the petroleum can be used as a carbon source. And very analog to vegetable oil. So the microbes would use the petroleum as a carbon source and respire on the chlorinated solvents as an electron acceptor. I would say that I would try to estimate this. I'm brainstorming here. This is far. You should take this with at least a grain of salt. But if you can estimate the rate of degradation of the chlorinated solvents by some independent means, perhaps the production of chloride in the groundwater, then you might be able to estimate an order of magnitude of the chlorinated solvent addition to this fossil fuel carbon and subtract that from the total. If you're interested in this question, you should download our report by Thomas Boyd. It's a NSZD document. He talks about the use of carbon isotopes for estimating the degradation of chlorinated solvents. In fact, we're doing a pilot study with him to see if we can measure the CO2 flux from chlorinated solvents. I think it's a long shot, but we'll see. The data will speak by itself. Okay, another question. This seems to be a tricky one. 44 inches of precipitation per year, perch water in sand with clay layer. This is a very challenging question. I don't know. I don't have a good answer for that. It depends what the pattern is. If you can give the traps a 3-day period where there's an open flow path between the source and and the surface, then you might have a shot. Otherwise, this is a difficult one. I think this is getting too specific. I would love to chat with the person that formulated this question and see if we can think of something. It's going to be a challenge. I need to disclose that. The last question, we're now here on the hour, is will this webinar be archived anywhere for future viewing? Yes, we are recording this webinar, and we're planning on making it available and to people that couldn't attend this, or the attendees if they want to refresh their mind. And I just want to thank you all for sticking to the end of the call. And if anybody has additional specific questions, or they just want to chat about the site and see if there's site-specific challenges, such as the 44 inches of water at the site, I'll be happy to chat with you. We always try to make sure that people have a good shot at getting usable data and identify site-specific conditions that might not make it the best choice. But I want to thank you all for attending. It looks like everybody really stayed until the end. And you will be prompted for a survey at the end of the webinar. If you have a couple of minutes, we accept all kinds of feedback. It doesn't have to be good. As long as it's candid, we will take it. Having said that, I appreciate your attendance, and thanks for thinking about natural source and depletion and sticking to the seminar to the end. Thanks again. Bye now.